Hello, it's Keith here, and this is lesson 2 of the SuckHunt series of my ARM assembly programming tutorials. Well, what's SuckHunt? Well, if you don't know that, then you didn't see the previous episode. SuckHunt is the little shooter game you can see here. It's very simple. We just have to move our cursor and shoot bats before the time runs out and they bite us. So it's basically just a simple test game, and it's available for download on my website, and I'm porting it to various systems. On the ARM, I'm porting it to the Game Boy Advance, as you can see here. The Nintendo DS is already working, and I'm planning to do a RISC-OS version, hopefully. And basically, most of the code between these will be pretty much the same, give or take the odd slight tweak. What won't be the same, though, is the graphics routines and the joystick routines. And so that's what we're going to look at today. We're going to look at the Game Boy Advance version and the platform-specific code that has been written for that. Now, if you need to see the general code, please see the previous SuckShoot episode 1, which we covered that. Okay, well, let's go over to the code and let's see what we'll be looking at today. So we're looking at GBA SuckShoot once again here, and we're going to be going over the parts of the code that are specific to the Game Boy Advance. Now, the first thing we need to sort of discuss is the graphics data. Now, we have, if we see it, where is it? The graphics data is in two parts. We have the sprite base here, which is a file. Now this is all of the sprites of the game, and then we have a sprite info table. And in this version of the game, it uses 8 bytes per entry, and that's 8 bytes per sprite. Now this is all created and edited and exported with Sprite Editor, as everything is in my tutorials, and it's my free and open source Sprite Editor. So here are the sprites. So the first one is the crosshair. The second two are the bats, 2 frames of large bat, 2 frames for medium bat, and 2 frames for the small bat. And we can export the details of this if we go to the sprite list option here, and we use the export info option here. That will export the sizes of all of the sprites, and that is what was used to create this table here. I just had to pad it out and convert this part to a long because it's designed for 16-bit programming, not this amazing revolutionary 32-bit weird stuff that we're looking at today. So that's the table that is used by our sprite code. Now, our sprites are called at various points, and you can see we've got some information with regards to the enemy sprite, and these will be used as parts of the drawing routines. Now, the player sprite is very simple. We just show the sprite 0, the first sprite in the table, at the position of the player. But the enemy drawing sprite is a little bit complicated because this uses what is basically a Z position for the current position of the bat, and that is used to select one of the 3 pairs of sprites, and then a frame of animation is added to that to select the particular sprite. So let's take a look at this show enemy routine. Okay, so we're loading R11 with the pointer to the start of the enemy data definitions. We're then loading a single byte for the X and Y position of the sprite here, and we're loading them into R8 and R9. And we're loading the sprite number, which is only going to be a 1 or a 0, into R10 here. Now, that is the frame of animation. We're basically then adding 1 to that, because the first sprite in our sprite definitions is the player sprite. So we need to skip over that, so we're adding 1 to skip over that. What we're then doing is we're loading in the enemy scale, and we're converting this into a format that we can use for our sprites, because we need an offset within our sprite table for the 3 scales of sprite. Because if you remember, our sprites are here, and we've got the 2 big ones first, then the 2 medium ones, and the 2 small ones. And so to select one of those, we are EORing so that we are working in reverse order. And we're taking these 2 bits here and we're shifting them to the right 3 bits. And this is effectively giving us an offset multiplied by 2 here. And so we're adding this offset here made by the scale to this offset here made by the frame number, and that will give us an offset within our sprite table. Now this is a numbered offset of a sprite number. We're then jumping to this show sprite routine here, which is adding that offset shifted to the left 3 times, effectively multiplied by 8 to the sprite info table. Why multiplied by 8? Well, because each sprite in our table has 8 bytes. 4 bytes for the offset within this bitmap data of the sprite, 2 bytes for the size, and 2 unused bytes that are just there for spacing to add it up to 8. Okay, so we're now reading information about the sprite itself, because what we're going to do is we're actually going to center the sprite. And what we're going to do is we're going to take half the width and half the height of our sprite and subtract that from the position we were passed to draw from. And this is going to allow us to draw our sprite basically centered on that past X and Y position. The reason we're doing this is it's important so that our range checking routines will work from the center of the sprite rather than the top corner, because we're drawing from the top corner, but we need it to be the center for the calculations. That's what we're doing here. We're loading in the width of the sprite, shifting it 1 bit to the right, effectively halving it, and then we're subtracting that from the X position. We're then loading in the height, shifting it 1 bit to the right, effectively halving it, and subtracting it from the Y position, and this is effectively centering our sprite. Now, what we're going to do next is we're going to calculate the memory address in VRAM that we need to draw our sprite. So the VRAM base is at that address there, which is far too long for me to pronounce. We're then basically calculating our X position multiplied by 2, because there's 2 bytes per pixel. We're then calculating our Y position. There's 240 pixels per line and 2 bytes per pixel, so we're multiplying our Y position by 240 times 2 here. We're adding these to the base of the VRAM, and that is calculating the start and corner of our sprite. We're then loading in the address of the sprite bitmap data into R1 here from R11, which is pointing to our sprite info table. So that is the offset of the bitmap data for our sprite. And then all we're doing is we're transferring the data of our sprite in words here, EORing that with the screen, and that's an inversion trick, so that if we draw the sprite the same position twice, it will be removed. We're repeating until we've done each line. We're then adding 240 times 2 to the starting address of the line. So we're basically starting here, we're drawing our line, moving down a line, drawing our line, moving down a line, drawing a line, and so on. It's basically the same as the simple series example. It's just it's EORed now. I don't think maybe it was originally, but it is now, and that is just going to draw our sprite to the screen. So that's the sprite drawing routine. What else have we had to specifically do? Well, there's not too much else that's platform specific. I mean, at the start of the code, we've got the initialization for the stack pointer and for the video, the screen, but this is all basically the same as the simple series. We now have a clear screen routine. You can see this here. It's a very simple one. We're just loading the base of the screen, the size of the screen divided by 2, and that's because we're writing 2 pixels at a time by storing 32-bit words each time. And we're just repeating until we've filled the screen. The print char routine is the same as the simple series, so we're not going to cover that. What we are going to just very quickly look at is the joystick routine, because we have a nice new joystick routine. In my tutorials, I typically use a standardized format, which is up, down, left, right, fire 1, fire 2, and then fire 3 and fire 4 if available. And so that's what we're converting to here, and this is going to make porting my game to other systems more easy. So what we're doing here is we are loading in from the port of the joystick as we did before in the simple series, but what we're doing this time is we're basically masking off the bits that are related to the directions and then shifting them into the correct new positions, and we're ORing those into R0, which is going to be a build-up to build up our data. So we're effectively converting from this, which is A, B, select, start, left, right, left, down, up, into my standardized up, down, left, right, fire 1, fire 2, select, start. So that's going to make things a lot easier for porting this to other systems, because while the Game Boy Advance and the Nintendo DS might do things in the same way, RISC-OS is going to do it completely differently. And so by standardizing on a common format, it makes it easy not to only port between ARM systems, but when I come to making a new game, and like in this case, this is ported originally from the 6809 and then to the 8086 and then to this, it takes a lot less time for me to think about porting it and a lot less debugging if my joystick routines work the same on all the systems. So that's what I do. Anyway, as I've already said, you can go to my website and you can download today's example code and you can have a go with it and do whatever you want with it. As I say, you're welcome to use the code in any way you can. Now, if you've liked what you've seen, please like and subscribe. If you like the videos, YouTube recommends them to more people. And if you don't, I fall into a pit of terrible despair. If you subscribe to the videos, you'll see what's coming next. And what is coming next is the Nintendo DS version, hopefully a RISC-OS version as well, if I can be bothered to port it. So make sure you like that video, otherwise I might not. Anyway, thanks for watching today, and goodbye.